Welcome to finite element modeling. We'll be learning how to model a 3-point bend and 4-point bend test configuration, which are very important tests in the characterization of composite sandwich structure failure. I'm inviting Fadhel, who is going to guide us through this tutorial. But before I do that, I want to walk you through some important points. The 3-point bend test configuration is governed by the ASTM standard C393. It's a flexural test that's of a flat sandwich construction. And the idea of this test is to measure the core shear strength capability. The dimensions are provided in the test procedures. And what we have really here is a roller support here, a roller support here, and a load applied in the center. And what that does, it creates a section here between the rollers that's constant shear force. And so that causes the stresses in the core to be fairly constant, but also when you apply this load, that'll be the critical failure mode of concern. So this test does a very good job of predicting core shear failure and is used in the design of these kinds of constructions. Composite sandwich structures really are made of a laminate on the top face sheet, and in the middle you have a core, and the bottom you have a face sheet. So this sandwich structure construction improves bending performance, is used in a lot of different applications, including surfboards and many other structures, such as launch vehicles. In this case, the face sheet material is provided as carbon epoxy, and the laminate of the top face sheet is provided as 045-45-0, meaning that the plies, the fibers are oriented in this direction, the X direction. The 45-degree ply is oriented 45 degrees from the X direction, so it's rotated. And then you have another ply at 45, and then finally you have a 0-degree ply. And it's a woven composite, which means I have equal number of fibers in the X direction than the Y direction. And I'll have Fadhel go over the discussion of how the modeling was done. The 4-point bend configuration now is one where the rollers are apart like this, and the load is applied in the inner rollers on the upper face sheet. What that does, it causes a bending moment that's uniform between the inner rollers at the top surface. And because the bending moment is constant, it produces a compression stress on the top face sheet that is very useful to use for predicting failure of the face sheet in compression. It's a very good test to characterize the compression capability of a face sheet. With that said, I'll now transfer over to Fadhel. Thank you, Fadhel. Appreciate your time.
My name is Fadhel Al-Safar, and I'll be introducing the Abaqus tutorial today. I'll be running simulation for 3 and 4 point bending test of composite sandwich structure. We'll be implementing ASTM C393. We'll be implementing ASTM C393 standards to test composite structure, in which we will calculate the transverse shear in the core material, which is an important aspect of the composite structure, and has it's susceptible to fail in shear. So we'll calculate the shear stress within that within the core, and we will be using this relation here, this simple relation, to calculate the shear and comparing it with the results that we obtain from the simulation. This is the first problem that we'll do. The 3-point bending test, in which we have 2 supports on the side with 1 load in the middle, and the problem is symmetric. The material we're using is carbon fiber epoxy for the lamina with the with the orientation of 0, 45, 45, 0 of woven fibers. The, the core we'll be using has is a simplified model of the core, which has an isotropic property of 10.877 psi and plus 0.3. We'll be showing through this example how the shear through how the transverse shear through the core is quite uniform, as can be seen through this shear diagram. From modeling perspective, the approach that we'll be using for both of the experiments is that for the core, we'll be using 3D solid elements, and for the lamina, we'll be using a shell element, in which the shell element it's quite useful for structures that have quite long dimensions in two dimensions, and the third dimension is small with respect to them, which is the thickness in this case, which perfectly match for the case that we have now. The second problem that we will be handling is the 4-point bending test, which is this one here. It's again a symmetrical problem. It looks very similar, except that we have 2 points rather than one. And we have same material. And the things that we'll be showing is that in this problem, the area in between, the area between the two forces has a zero shear stress and the constant applied moment in between, which will result in constant axial stress in the middle, and the shear stress is very close to 0. The forcing region here would model as a small pressure area that will be applied here, and that the support here will be modeled, or this rigid here, the rigid part would be modeled as a simple support. Let's start now. Here is the Abaqus CAE. The first thing, once you start, that make sure that you set your directory well, so that you know where all your files are saved and you can easily recall them. Save the folder. And then the first thing we will do, let's just start with the model here, or let's navigate what we have here. In the top, we have the files and tools, features, in which we will kind of explore some of them as we go. This to handle and manipulate the picture and see it from different views. This is the kind of the workflow and all the process that you do. Most of them will be recorded here and saved here. And I think, yeah, we can start now. We'll start with renaming first. Let's rename the model here. We'll start the model. Let's rename it here, and let's call it here bending test 3 points. Oops, 3 points. For the naming, when you name it, probably it's better not to start with a number, because usually you'll get an error if you start with a number. We'll create two models, one model for the 3-point testing and the other model for the 4-point testing. So to create the other one, we go to here, double click, and we say, let's call it pending test 4 points. We'll start with the 3-point test, and the process will be quite similar for both. So it's just that the dimension is quite different. We'll start with creating the part by clicking on this part here, and the first part will be the core, and we'll call it core core parts 3-point bending, and it's a solid element, as you said in the beginning. So it is solid, deformable, 3D extrusion, and this is the approximate size of the worksheet that will be directed to. So it's good to have a size that's quite close to your dimension. So I'll have it as 15. And here we will start by drawing our geometry. So our geometry is, let's go back to it and see it again. So this is our geometry, and we'll do symmetry. We'll solve it in symmetry, which we'll cut it in half, and we'll solve this part here on the right. And we'll start by making the core. The core is the solid, so we'll draw this rectangle here, and then we'll make that shell element, and we'll see how to do it. So the dimensions here are 5.9 with in the x-axis, and the thickness is 0.75 inches. So you click here on the rectangle, and to make the shape here, you can either draw here directly or enter the coordinates down there. So I'll enter the coordinates here. If you take a look, it's here. I'll enter the coordinates and hit enter. This is the first point. The second point for the second corner, which should be 5.9 -0.75. You can enter it as positive. It's just that when I enter it as negative, it will go down here. So, and it won't pick up a lot of versions anyway. So that's our first part. Now it will ask for the depth or the extrusion. And in this problem, the depth we have is 3.94. So that's 3.94 inches. This is the first part. Let's create the second part. Second part is the face sheet. Face sheet part. 3 points bending, and it's 3D, but we'll use shell element, and we'll use extrusion here. You can do it multiple ways, but this is the way I'll do it. So shell element, extrusion, and then continue. Here we will draw a line, and then that line will be extruding it, and it will be a surface. And the shell element has no thickness, and the thickness is integrated within the element formulation itself. So the first point here, 0, 0, and the length of the line is 5.9, and the y point is 0. So that's the line. If you want to add the dimensions and make sure that you have the dimension, you click here, this point here, you go to the line, click, and you'll see that its dimension is 5.9. Click X here, done. And now it's asking about the depth. Again, it's 3.94. And here's our part here. We'll enter the materials properties, and then we'll go to the 4-point bending test. We'll make the parts, and we'll go kind of simultaneously. So let's go to the material properties. In the material properties here, we can enter the material from here, create material, and we'll start with the core material. And here we have many options. We have general, in which we can add density and other material properties. And then we have mechanical, in which we add the mechanical properties, elasticity, plasticity, other damage models. But today we'll do elastic here. With the elastic here, we have for the core, it's isotropic material. There are many options, but we're using isotropic material. And this, the Young's modulus, what we have is 10.877 PSI, and that's 0.3 Poisson's ratio. Okay. Now we created the material. We need to create a section then. We create the section for the, again, for the core. I'll call it core section. The core again, it's solid. So it is solid, homogeneous, continue. And here it's asking you about what's the material of that section. It's core material. So you should actually start with creating the material. If you start with the section first, it will ask you about the material. And if you don't have it, you won't be able to enter anything. So, okay. We're not done yet. We need to assign the section now. But to assign the section, since this is the face sheet, we need to change it to the core. So if you go here on the top, you can see here it says parts, and it says bending test 4 point. So I was entering the material for the 4-point bending test. That's still fine, but let's move to here and. Oops. Just a second. Seems that I created the material for the first part only. So I'll add the material again. I mean the parts. I create the parts again. Yeah, it seems that I started with the 4-point bending, but I entered the parts for the 3 points. So all I'll do is just I'll change the name here. So 3 points. Okay. You cannot have this one here. So 3 point test. And this I'll call it the 4 point, since I haven't added anything in there. Now we're ready to start again. So that's again that. So this is a 3-point bending test. Sorry about that. So just to keep it live, we need to add the material properties again. Now we created the material here. We created the core material. We created section here. We created the section. Once we create the section, we need to assign that section to certain material, to the geometry, and that's what we're doing here. So you go to here, assign section, you click, and then you have the core section here. So that's what I said before. You need to have this one first. So now once it's a green, it means that now you assign the material. You assign the material to the geometry, and you're good to go. Let's go to the face sheet now. For the face sheet, we create the material again, face sheet material, and elasticity, elastic. Now it's lamina, it's not isotropic. And the material properties that are given here is, let's just take a quick look here. It's 11 E6, so that's 11 E6, 11 E6 0.05, and that's 0.5 E6. G13 and G12 was not given originally in this problem, but this problem is a plane stress problem, and these two does not have much effect on the problem. However, you need to add them for the solver to get the solution. These values are usually 60% of G12, and that 60% is calculated as 0.3 E6, 0.3 E6. So that's the material. Now we're done with this. Now this system is quite different than the previous one because this is a shell element, and its section assignment is quite different than the solid one. To assign it, we go to here, this one here, and it says create composite layout. You click on it, and let's call it here face sheet layout. And here you can select the different element types here for assigning that composite layout. And you can choose the number of layers. We're supposed to have 4 layers here, but I'll put it 2 here, and then we'll click an option to make it symmetry. So in total we'll have 4. So continue, and this is the option here. But let's add these properties first. So first, it asks you to select the region. You can right-click, edit region, and from here you can select that structure. Okay, and here once you select the region, you can see here reference. It's the direction of the reference with your coordinate systems. And this is small number here, 1 and 2. This is the orientation of the fiber. So 1 is the orientation of the fiber. If you change that angle if you add an angle at 45 or 90, you see that this number 1 will be changing with respect to the reference frame here. And we'll see that. We'll make a kind of a plot chart, and we'll see that the orientation of the fiber. Edit material, we have face sheet, click, thickness, again, right-click, edit, 0.01, that's the thickness that's given in this problem. The angles for the first one, for the first apply is 0. The second apply, its angle is 45. So if you take a look here, once I entered 45, and you look at this, it's shifted to 45 angle. Now, before I'm done, just click on this so that it's symmetric structure, and click OK. And you can see here it turned to green, which means that we're good to go here. So now we assign the part and material property. We'll go to assembly, in which we'll create these 2 parts. Now we'll assemble them. We'll put them on one single geometry or one single part, so that later we can run the simulation on all of them. To do that, you go here, create instance, click on it, and here these are the parts that you created, these 2. And it's fair to choose independent and have auto offset so that you can see them separately here. apply. Okay, once you click apply, that's enough. So that's, you don't need to click OK. Now we need to move this lamina on top of the core. And to do so, if you go to the left here, you can say translate instance. Click on it, and it says select instance to translate. And we want to translate this one, so we select it, and then it says select the starting point. We need to start from this point, and then it's asks you where's the end point. We want to end here. If you click on it, it will translate it, and click OK, and it's done. We need to do one more step here, however, is that we in our structure we have two laminas, one on top and one down, and the one what we have here is one single one. So what we can do here on this step is to go to here, linear pattern, and click on it, and then it's kind of doing a symmetry or copying that layer, and we will have a second layer. But before that, it's really good to get familiar with this option here, with this feature. Here, as you can see, once we added these layers together, it's hard to see which is which. So if you go to here, it says remove selected. You click on it, and then you select you go to here, down there, and you select what faces or cells that you want to remove, or you want to hide, not remove. So I'll say cells here. You click on it, click in, oops. So you click on it, and then click enter, and you'll have that one removed, or hidden now. It's hidden now. So click now, done, and we go back to linear pattern. Click on this one here, and okay, and you can see here it gave you 4 sheets here, but we only want one more. But that's because it's copied around X and Y. We do not need around X. So direction 1, we do not need it. That's X. We want to copy it around Y. And the offset should be the thickness of the core, which is 0.75 inches. And here you want to make sure that it's copying to the top or to the bottom. And you want to see this. Here is the core, and it copied it to the top. So we wanted to move it down, and to do so, you just click on this one, flip, and now it went down. Okay, and now we are done. We have it. If you go back and you click on this one, you hide the cell, and if you click on this, it will show everything. So you click this one here, and you can see how we have 2 layers here. After this step, we can go to step to create a step here, and this is the step in which it says that it's a static problem, it's a dynamic problem, and so on. And plus we will output we'll decide what are the output parameters that we want, stress, displacements, or strains. So let's call it load applied here, or apply load static, continue, and here I believe for now we do not need to change anything. This is just that the minimum increment size and maximum number of increments before the software couldn't solve the problem, it will kind of give you an error. And Probably we can make this one here 0.5 so that we have a bit more steps. And then one more step here that's important is to go to output here. Output, field output manager, and to edit or create one. So it's you can do either. So when you go there, we decide what are the parameters that we want here. What the parameters that we want to extract here. Want the stress, okay, strains and displacements, maybe forces, contact, not sure, but we'll leave it. And here it should give you, when you simulate it, it will give you deformation into steps, so that it will act as if the things are moving into steps rather than moving from no deformation into complete deformation. And here the extract point. When we are doing shell elements are integrated into certain number of points, and when you assign the composite layout, we had 3 integration points. So in that point, the first point on that layer is the bottom. The second is the center, and the third one is the top layer on the shell element. But we want the second one for each layer. And to do so, we select the second integration point, just like here we're saying we need 2. For the second layer, we move to the second layer of the second element. So we add 3 and 8 and 11. So that first layer, second layer, third layer, and fourth layer. And for all of them, we're taking the middle integration points. And okay, we can go to history output. Here these kind similar to what we did before, but here we only need new displacements. There's no need for this one now, so we can skip this one for now. Now we go to the interaction here, in which we haven't assembled dot layers is not enough. And if you run your model, you either get error, or you'll see that you can your geometry can penetrate each other. To prevent that, you need to assign contact conditions. And to do so, we'll do some, very simple things. There are many options, but we'll do simple things today, which is create a type or constraint type. And the way to do it is to go here, create constraint. I'll call it top type, enter, and ask you to select a master surface. Select. I'll select this one here and click done. And I want to connect this one to the core. So here it specified the direction. So even though it's the shell element does not have a thickness, but it has a surface. It has 2 surfaces, top and bottom. And what we want the bottom surface, which if you rotate this one here, you can see its color is brown. And it's asking here, do you want purple or brown? We want brown, which is the bottom one. And now it's asking about the second the second surface, which is it's called slave type. So we say we want surface, but we want the core now. I click on this to switch, and now I choose this surface so that it's not that these 2 surfaces should be tied together. And then here we click OK, and you'll see this, which means that it created something here, which is the type. We'll do that with the bottom layer as well. So we'll call it bottom. Type. Again, we'll do the same thing. This is the bottom layer. Click on it. Done. And now we want the purple one. We want the one on the top. Now it's asked about the second layer, surface, and flip it. We want this surface here to be in contact with that surface. So again, no need to change anything for now. And now we created the contact. We need to move to the load and boundary conditions, but before that, we need to do something. We could have done it earlier, but we can do it now, which is here the load is applied at this point here, and the support is applied here. So I need to kind of split my geometry so that I create a line so that I can apply my force or apply my boundary condition. And as I said here, the load, I'll create a small surface and apply a pressure on it. To do so, we again, I'll hide this one here so that it's easier to work. Oops, show them all and click here and done. And what I want to create like a line or split this face to have small area. And the way to do it is by clicking into this option here, one single click, and it says partition face sketch. Click on this and then select a face, which is this face, enter, and then it asks you to select an edge. Any edge that will be shown when you click on this. And so that's the edge that I clicked, and this is the shape. So basically, I will just create a line, and that line will cut this face. So if it is just like in this case, 2D, a line is enough to cut it into two surfaces. And here I will add a dimension. The surface of the applied pressure, I'll have it to be 0.2 for 3-point and 4-point testing, the bending test. So that's a line here. And then once I have it, X, and then done. And that's the surface here. It's created here. And I need to create a line so that will act as a place to apply my boundary condition, my simple support. So the way to do it's exactly the same thing. I have this one highlighted, but I want to do it at the bottom surface now. Click on this and select an edge. Again, line can be anywhere, since I'll add the dimension, connect, and then if you write anything and you want to raise it or you want to delete it, you can go to this here, razor shape, and you go to that and delete it. Dimensions, and here the dimensions here between my support and the edge is 1.1 inch as shown here. So that's what I have here, 1.18, and click and done. And as you can see here, we have it created here. And I think now we're ready to go. We're done with the step and the interaction. And it looks that like sometimes when you cut the object or so, just make sure that that nothing has changed and it's still valid, because sometimes changing anything in the geometry will affect your results and you need to retry or reassign the surfaces again. Now, boundary conditions on loads. So we want to apply loads, loads on the to act as the force that's applying the bending force. So I'll call it pressure load, and we'll go to pressure here and click continue. And they want to apply it on this small surface that I created, which just zoom in, select it, and done. And then it asks about the area, and it's the purple, in which if you select the brown, then it would be the bottom surface and it would be perpendicular to the bottom surface. The pressure magnitudes here, basically what I'm planning to do is I have a 100 pound force in mind that I want to apply, and I choose the pressure area that I select, which is the width times the area that I selected here. And the pressure is defined as force over area, and I have this 100 here, so I'll divide force over area, and they have this on 128.2 psi. So 128.2, and I have it created like so. And then we need to create supports. We need simple support and we need symmetric boundary conditions. So boundary conditions, the boundary condition to assign it, you go to here. It's either you click on this one, so it will create right away, or it'll give you the boundary condition manager. If you click on it, you click create, and it will direct it to this window. Let's call it symmetric boundary conditions. And here in Abaqus, there's an option to apply directly a symmetric boundary condition. So we'll use this option here. We'll click on this, and the symmetric boundary conditions are applied here on the edges. So on the edges and on the core. So to make the selection easier, we'll go to here, in which it asks what you want to select. And you say, I want to select edges, and you come here, you select this one. If you want to select multiple objects, you click on shift, and then you select the other one. If you didn't click shift, then it will you will not be able to select both. And then we want to select the face of the core to apply the boundary condition as well. So here I will select face, and I want to rotate it because I want to see this one. And the way to do it is by clicking on this. Again, clicking on shift and choosing this face, and then done. Now, after clicking done, it's asked you what are the boundary conditions that you want to apply. What's the symmetric boundary condition that you want to apply? And we have our symmetry around the x-axis, which is this one, in which the u1 will be set to 0, and rotation about y and z will be set to 0 as well. These are the symmetric boundary conditions. We did so. Now we need to apply the simple support. So I'll call it simple support, displacement, rotation, the second one. And now let's shift again to the simple support is applied to the lower lamina. And let me here select edges. And this is the line that I created earlier. Choose it. And the simple support is acting around on the y. If you look at this, so this y on the top. So y should be 0. So that's kind of the physics behind it. So so that's 0 now. And by setting that, I believe we're done now with the boundary condition, and we're ready to go to the mesh. On the mesh here, we looking at this here. This is the lamina, and this is the core. And one of the things that you notice, this one is green, and that one is pink. And and the reason for that is, sorry. The reason for that is you can have structured regular mesh or free mesh that's not very structured. And usually structural mesh are better, but you're not always capable of achieving that. However, in this case, we can do that. And the way to do it is by going to here, assign mesh control, click on that, select all, enter, and here you can change the element shape here. And well, I'll change quadratical, and we'll change the technique to structured. And you can see once you click structure, and here you have the green color here. Once you click OK, it will turn green, which is nice. See it part. And now we're deciding the number of elements here, or at least the size of the element. You click on seed and then done. And here it asks you about the approximate of the global size. So here I'll set the approximate global size to 0.1 inch. Apply. Okay. And now we can click on mesh part. So we can mesh the lamina now. And then we'll go to mesh the core. So once you do that and click OK, it's meshed and it looks nice and well structured. If we click on this again, we'll have the other shape, which is not meshed yet. So I'll do the same thing, and I'll have the same number of elements, of same approximate size, I mean, not sheer number of elements. And okay, now we're done. We can mesh it now. Done. Here, before we move on, I just want to make sure that you notice that here at the bottom we can see here, and it's kind of gives you an update of the things that you do. So once we created the elements on the face sheet on the lamina, it gives you the number of elements that were created. And then here is the core section. We created elements, and it shows you the number of elements that were created for the cores. And you can see for the lamina, the shell element, number of elements is really small compared to that one, because there's no thickness for that one, and the thickness is kind of built in within the element formulation. And that's one of the reasons that shell elements is usually faster in computation, because it consumes a lot less element number, and its thickness is kind of integrated within the elements. But you want to make sure that you can actually use it for whatever application. So now we are done with the element, and we're kind of ready to go, hopefully. So we set our part, we set the properties, we finish with the assembly, we set our step, interaction, yes, load, yes, mesh, yes, and then let's go to job. Once we go to job, we go to here, create job. And here it asks you to create, to give the name. So I'll say bending test, 3 points. And here at the bottom, it's asking about the source. So it's either a model, which is what we did, or an input file, which is kind of similar to homework one. You write your own input file and you insert it through here. And here at the bottom, it's asks you to select the model that you want to use. Since we created 2 models, 4-point bending test and 3 points, you can see them both here. So now we finished the 3-point bending test. So I'll click continue here. For now, you don't have to change anything here. Okay. So you need to go back here and to go to job manager. You click on that, and this is what you created. It's here. Here it's the good thing that here the simulation is not run yet, but before we run it and click submit, usually it's a good practice to start with data check, especially at the beginning, because that kind of gives you kind of a feedback of what's happening. So you click on that, and it will take some time as it go through it, and you can click on monitor here, and it will show you the things that are happening here. And it will show you if there's an error or if there are warnings or so. So if you look here, you can see that I do have some warnings, and some of them are coming because uh, as I set my my extraction points and on the output field to 2, 5, 8, 11, these are extractable for the shell, but not for the core. And I believe that's what it's saying. What it's saying here. So here the check is complete, and that's good. We have no errors. We can submit now. So let's submit it. And as it submit, we can do the same thing. We can go to monitor and observe that if there are any errors, if there's any warnings, and so. Now let's go back to our model as that one is running, and just like kind of review and see what we expect to have. So we modeled our structure as a solid element and a shell element for the lamina, and here we draw the shear diagram here simply, and that's the shear diagram, and we expect to have kind of uniform shear stress around the cross section of the whole structure. And one of the things that as well that have been done, this is the formula that we've taken from ASTM C393, in which the total force applied here divided by the width times the cross section of the core plus the lamina, that's C plus T. This one will give the shear stress or the transverse shear on the core. So that's kind of one of the checks that to see if our results kind of match with what we expect. So we expect to have results that's quite close to this one, 30.9 psi here from the in the core. So let's now go back to our model, and it's complete yet. It's complete now. So we click on results, and on the results here, to see the deformation and what happened, we can go to here and click on plot contours. So that will show you the deformation that happened. And if you look at that, it looks weird now. And the reason that it shows you that the stresses on both the lamina and the core. And what you need to do, and the stresses on these two are not the same, it's different. So one of the things to do is to go to here, remove selected, just like what we did before, and now go to here at the bottom. Now the name is changed. Now before it's called cells, now it's sections. So you click on this and click done. Now you can see it. So that you can see it's nice and uniform. One of the things that you can do as well to see it better is to go to here, common options, click on it, and it will give you a few options in which to change the view and have a bit how it looks. And you can click here on free edges. If you click on that, you can see it in this form. One more thing is that if you want to exaggerate and make the deformation larger, you can try this option. here in which it will exaggerate the deformation. For example, if you click on this and you click apply, it is the standard one, but if we do this like 20, you can see here the deformation is exaggerated now, but we'll use the auto one. So now what we want to see, how the stresses look like. Now let's go to the S11, S22, and see the shear as well. So one of the first checks to see is that when we have this this kind of test, a bending test, what we expect to have is to have tensile stress at the bottom and compressive stresses on the top. Since it's bent on the top, so it's kind of, we have compression on the top face and tension on the bottom, and that's kind of what we see here. If you look at this section here, you can see these values here are negative, and at the bottom the values are positive, which means this is tension and this is compression. And we can see the stresses on these layers, and to do so, we can go to results here on the top, results, and we go to section points. Click on that, and here you can see categories and applies, and click on applies, and here you can see apply 1, apply 2, symmetric apply 1, which is the symmetric apply 1, symmetric apply 2, which is symmetric apply 2. So you click on this, and now you see the stresses on apply 1. You click on this one, you see now the stresses started to change, because now we're seeing the stresses on apply number 2, which is the fiber are directed at 45 degrees. You click at apply number 3, and that's what you see here. And you click on apply number 4, and that's what you see here. Now we want to see the core. We want to see the shear stress on the core and how it looks like. To do so, let's switch this here. Oops, since we are showing the plies, and all that you need to go to here and click apply. Now we can see it. We're showing the view for the plies. So here's here's the core, and now we're seeing the shear stresses on the core. And if we look at the maximum values here on the core, we can see a value of 36 psi. If we go back to our slides and our calculation, we see that the values that we have here is around 31, and the value we obtained here is around 37, which is quite close, which gives a good sign that this gives a quite approachable results, or results that make some sense. And it's always important to make some sanity check when you run your simulation. And we can now see as well the section. We expect that to see quite uniform cross section stresses on the cross section. So if we rotate this one here, and you take a look at the cross section here, you can see here the values of the cross section here. It's the light blue and dark blue. We have quite small values at the cross section here, which is quite small and uniform values, which is kind of what we expected from this one here. What we can do as well, we can take a cross section. Can take a cross section here. If you click on this, to show you the cross section. And then if you click on this one on the right, you can now move the section here just like this, and you see how the stresses change inside. So, and you see that we kind of have quite uniform stresses. That's not changing much. If you want to plot these results and see, one of the options to do so is to go to Tools, Path, Manager, and then click on Create. And let's call it shear path 1, and click on Continue. And then what we can do is to go to this face, and let me make it normal to this face. So that face is the YZ. So it's this face. I'm probably clicking on to this one here. So now I can actually go to here and click on the surface directly, and you can see that a path is being drawn here on the surface. And once you're done, click Done, and click OK. You can see it's added here. In order to see it, you need to go to this option here, Create XY Data. Click on that. And on this option, go to Path, click. You can see this what I selected, and then select Plot. And now you can see the plot of the you can see the plot of the shear stress on the values that I selected. And you can see that it's quite uniform. It seems that there is a point here that's off. Maybe I selected by mistakes, but now you see how to do it. One more thing that we can do here is let's turn off the section. As you can go to Tools, Query, and select this one here, Apply Stack Plot. If you click on that, now we want to see the ply orientations, and here we have the core, which doesn't have a ply. It's not composite. We modeled it as as isotopic material. So let's change this one here, and now let's click on this. And what we see here, this the structure of the composite that we created earlier here in the layer. And you can see here the first layer is 0, and the fiber is oriented this way. Second layer 45, third layer 45, and the last symmetric layer is 0, which is 0, 45, 45, 0, which is what we did. It might be as well nice to include it in a report or so. So that's how you get it. One more thing that we can do is if you go to here, plot material orientation. Now you can see the material orientation. That's kind of another view. And you can see you have a woven composites, and you can see here now we have the top layer. We have it as wait, let me go to here again. Section points, applies, this apply. Now you can see this one. So you can see that two layers that are perpendicular to each other. And if you go to apply 2, you can see that now it's deformed. That's 45. If you go to symmetric apply to, which is the third apply, it's again 45. If you go to here, again, this is now at 0 degrees. So that's good. So now we run our simulation. We did the post processing. We saw the stresses, and we saw for the core. We saw for the core how the shear stress is quite close to what we calculated. What we want to do is go back. We want to just turn off this one here. The way that the core is not showing, because it's set to Plies number symmetric, which and the core does not have this one here. So we can do this, and now we can see the core. So that's good. Now we passed by this problem. We look at the cross section. We looked at the shear stress, and it was it had a value that's around 37, which is quite close to this value. And now we want to move back to the 4-point bending test and see how it looks like. And what we will see, we'll see that how the shear stress in the middle is quite 0, and due to the constant moment in the middle of that point here, we'll have constant constant S11 stress, which is the sigma 11. So to do so, let's go to part, and from here you can change the part from, I mean the model sorry, from 3 to 4. And now we can create the parts again. We'll do it fast, and it'll be kind of a summary of what we did. So we'll start with the core part, and it is solid 3D, and we'll start with 0, 0 here, and look at the geometry that we have here. So we're making a symmetry. So now again we're drawing this part here, and I will add 2 inch here to the right as a buffer here, so that it looks like this one here. So we'll have 9 plus 2, that's 11. So that's 11, and the cross section is again just like the other one, which is 0.75, and it's created here. You can click this one if you want to like modify it, and it's fine if it went behind this point here. So click X, done. And now the depth in this problem, the depth is 3. So this is the first part. Now we'll create the face sheet. Face sheet. And we'll use shell element, and we'll use extrusion again. And we'll use line at 0, 0. And we'll go all the way up to 11 and Y0. And you can see it here. And then, oops, no, done. And the depth is 3, and now we created sheets. Very similar steps to what we did before. Now we're done with the part. We can go to the property, and now we'll start to creating properties here. Create. We start with the core material, mechanical, elastic, isotropic, 10877, 0.3 Poisson's ratio, done. let's create the face sheet material, mechanical, elasticity, elastic. For this one, it's lamina. And the value is just like the last problem, which is 11 E6, 11 E6, 0.05 new, just Son's ratio. And this one, 0.5 MSI, so that E6. This one is 0.3 E6, 0.3 E6. And done. Now we create a section for the core. So core section, and that's solid, homogeneous, done. And create this one, face sheet, core material. Now we're not done yet with the core. Let me just bring the core here from the part. And we need to assign the section. It's not green yet. So it says here, select the region, select this core. And the material is, or the section is core section. And the material is core material, and it's written here. Now it's green, so now we're good with this part. Now we need to move to the second part, face sheet. For the face sheet, it's composite, and we're modeling as a shell. So we'll go to here, create composite layer, and we'll call it face sheet layer. Conventional, 2 layers, because we will use symmetric, and in total will be 4 here. And right-click, select the region. Make sure that the reference and your number 1 is as expected. Now it's along the x-axis, and that's what I said it to be. Face sheet thickness is 0.012. So that's the thickness that we have for this problem here. So that's what we have here, 0.012. And done. The rotation, the first one is 0, the second one is 45. And if you remember when I spoke about the integration points, when we took the outputs, these are the integration points here. So you consider the 3 or 5 integration points per element, which may add some more accuracy to the calculation, but we'll leave it as it is. So now, okay, now it's green, so we're good. We can move assembly, just like what we did before. We'll assemble the 2 parts and auto off, so that we can move them easily. Translate, select this one, first instance, and then select the starting point. So I'll select this one here, select the second point, and I'll select this one here. That's good. And now we need to create the linear pattern. So, and it's better to hide this one here. Enter. So select the instance. I want this one here. I want it only along the y-axis. So put this one to 1. Direction 2. The offset is the thickness of the core, which is 0.75. Make sure that you're offsetting in the right direction, and to do so, in doing so, just have this one here. So it seems that we're on the right direction. So click done, and let's make sure again. So yes, we have these 2 layers, and now they are on the right direction. We want to split it just like what we did last time, but we changed the location. So we'll go to here, split. I'll choose this layer here on the top, enter, select select edge. What I want to do is that I want to create a small area to apply this force here, and then I'll select a line which would act for the supports. So this one from this edge is 4 inches, and from that from that edge it's 7. So this line here, and adding a distance. I want this distance to be 4 from this line. And now I'll add another line to act as so that it create the surface that will apply the force on. So now I need to take the measurement. I need to take this one, and I set it to 0.2, and done. Nice, I have it here. So for the second one, we do the same thing. So, and it's already selected, so I'll go to this one here, the done right edge. We have it here, line, draw, and dimensions. And this distance is 2 inches, so that's the buffer that I added and originally. So that's 2 from that edge. So that's 2 done, and I have this one. I have it, so that's good. Now let's move to the step and then the interaction. In the step, just like what we did last time, load, slide, static, and this one here, it's 0.5, done. We go to the output manager, and here it's 5. And then we have stresses, displacements. Okay, good. But we'll specify the extraction at 2, 5, just like what we did last time, and 11, so that these are the middle surfaces of the middle integration points of the of the shell element for each layer, 2, 5, 8, 11. So dismiss, and then interaction. We'll do exactly just like what we did. We'll add the tie, so that's stop, tie, surface. I'll select this one, zoom in, this one, and this is the master surface. Click, and I want the one at the bottom, so that's brown, and I want to select the slave surface and select. We're not changing anything here, and then we will do it for the bottom surface tie. So select this surface for the master, this one and this one, done. And they want the purple, so that's it's spinning up. And now I'm selecting the core and the bottom of the core again. So I want this surface here, and then okay, it seems that we're good, and we'll go to the load now, apply the load, we have a pressure, load, pressure, continue. And the load is applied on the lamina, so it's not on the core. So it needs to switch here and zoom in so that we can choose this one here, and it's the purple on top, and the value that I calculated here is this one here, 166.67. So that's 166.67. Click and dismiss. Now we'll apply boundary condition, symmetric boundary condition, symmetric, continue, and I want to select the edges here, and yeah, these two. Don't forget to click shift. And then we need faces, but we'll shift to the core. I want to rotate it, escape and shift, and done. And symmetric about x-axis, just like the previous problem, done. And that's what we have. And now we need to add the simple support on the lower lamina. So that's simple support, displacement, continue. And I want to see edges. Select this one, and U20, click enter. And now we're good to go. Then we go here, we mesh it just like last time. It's pink. It just like it means that it's not structured, and I believe we can make it structured here, quadratical, structured. Click in there, and then global seed or approximate global element, and again I will choose 0.1 inches. Done, and I'll mesh it. Okay. Then I want to mesh the core, but first seed it. The approximate global size is 0.1. Enter, and then mesh it. And one of the things that you should have done, I forgot to do for the last one, is that to see better information about the thickness, we can go to assign element type here, close to this one here. And in here, the one I used before was linear element, but we can do, you can use quadratic element. And here, if you want to include more data about the thickness, we use full integration, which we uncheck this reduce integration. And then you can see here we have 20 node element, which will take more time for computation, but probably it gives more accurate results. So done. For mesh now, we're done with the part property assembly step, interaction, load, mesh, and now I think we're good to go to job. From here, we can go directly from the job manager, create, and this is now bending test 4 points. And the model is bending test 4 points. So we're good with choosing this one. Continue. Okay. And now you can see both models, the one we created earlier, and it's the model it used is 3-point testing, and this model, and the model that's saved is 4 points. So we start with data check, and hope that all things go right, but let's have the monitor on so that we kind of see what's happening and if there are errors, warnings. So the warnings are quite similar to what they had before as well for the extraction of uh, the points at 2, 5, 8, and 11 for probably for the core, which is this the element I used for the core. So that's to compare that's for the core, and that makes sense. So check, completed, submit. Okay. Let's go back to this problem again. Let's have a look what we have and what kind of we expect. So we have 2-point bending test. We have 2 forces applied here. We did symmetry. We applied it in this middle plane around the x-axis. We substituted this forward by simple support, and we had like a small area here, and we applied pressure on top of that, and we solved element for the core, shell element for the lamina, and that's kind of what we did. We went through the assembly step, creating the outputs, and then interaction, applying load boundary conditions, mesh, and then running the model. And in this one here, here you can see it drawn the shear moment diagram, and what you can see out of this is that something interesting about when you have the force drawn in this way is that the shear in the middle is actually 0. And in the middle, the moment applied is equal to 5p, but the important thing is constant. It's not changing, which should result on quite constant stress within this region, sigma 1 stress. So let's see that if it's done. So now it's done. Go to results. Let's go to deformation, and this now it doesn't make a lot of sense, so it's better to remove this part. So let's see them separately. So we can see their stresses separately. Let's go to sigma 1, and let's see what we have here. So these are the stresses now, and what we can see, we have we have tension on the top, tension at the bottom, compression on the top, and when we look at the value of the stresses here, and we're looking at the normal stresses, was probably affected by this one here. It's a quite uniform here, and probably we may can try to probe these data. But let's take a quick look onto the shear and the shear for the core. So this is the core, and what we see here from the core, first this here is almost 0. See the transverse shear. If you can see this dark blue, and you look at the forces here, it's 1 or 2. I mean not the forces, the stress is 1, 2 psi, which is very small values, and values that are close to 0. And that's what we have here within this region. So that's let's have it this way. Okay. So this way, it's kind of what we have. This is the first portion of this composite, and that's what we have here. And this portion here, it says here we have it at 0, and it's kind of what we have here as well for the shear. And the value of shear here, it looks like again quite uniform as well, which is kind of what we expected. We can look at the laminas, just like what we did last time, and see how the force is changing within the laminas for each layer. Layer number 1, layer number 2, and 3. These 4, not 3. These 3 actually. And these 3. This is for the shear stress. If we go to S11, this negative, positive. Let's look at this one here. It's kind of the same. Uniform, uniform, uniform. Let's see if we can actually see these values here. And can I do this? Yes. Yeah, here. So let's see if we can go to path here and create shear path to node third. And now we try to take these data and see if we can plot them and have a look at their values. Let's click at done. Okay, let's go to XY data path, and okay, that's fine. Let's see. We want to see part 2, and this is what I just selected, right? So yeah, they're quite consistent, and this change is actually small, so that's probably that's a change that on let me see. Seems that on here, probably that it was on different thickness, but in general that the shear was within this region was quite constant. And that's it, pretty much what we covered, and what I have. If you want to save data into your folder, you can use this probe function, in which you select it, and then you select it from view here, and then you go to here and you start to select. The main difference between it and between the path is that once you selected all the points that you want, you click write to file, and it will create a file that can be saved in your folder, the default folder that we set from the beginning. And for example, but one thing that you need to change the extension, for example, to CSV, so that it can be opened by Excel, or if you want to set like a text file, TXT, and then you open it. and you will get the values basically that you'll get out of this one is the one that you selected. For example, here we're selecting S11. The values that will be shown here that you recorded is the shear stress, the sigma 11 stresses or S11 stresses. And they're quite uniform here. If you look at these values, they're around 6,900 something. And one last thing is that we're saying that the core, we're comparing the transverse shear in the core. Oops, now I just need to change this one here. Yes. So if I go to the core and sigma 1, 2, and look at this and see, look at the maximum here, which is around like 46, and go up to the calculation that we did here, which is 39. You can see that the value is not that off from the max value that we're taking from this one here, which gives kind of good indication. So that's all that I have for this tutorial. I hope it was useful and hope that you enjoyed it. Thanks, and see you. Thank you.